In this lecture, we are going to study Bragg spectrometer. As written here, Bragg spectrometer was devised by W. L. Bragg and W. H. Bragg, a team of father and son, for which they got Nobel Prize in 1915. They received Nobel Prize for their services in the analysis of crystal structure by means of X-rays. So now let us look at the construction of this Bragg spectrometer. In the Bragg spectrometer, obviously, let me show you the X-ray beam. This is the X-ray beam produced by the Cooley's tube. This is X-rays and it is polychromatic X-rays. It consists all wavelengths. But in Bragg's law, as we studied in the earlier lecture, we need monochromatic X-ray. So the filter is used to get monochromatic X-rays. So here is the filter. What this filter does is, it filters out all the wavelengths but one. Only one wave is allowed to pass through this filter. There are different types of filter for different wavelengths. Whichever wavelength you want, you can select using the different filter. So here is the filter. Let me shift this filter closer to this X-ray. And then what we get is the scattered X-rays from the Cooley's tube. We need to focus it. To focus it, they are allowed to pass, this X-ray beam is allowed to pass through two screens, S1 and S2. Let's say this is screen S1, which has, this is actually a lead screen, consists pinhole at the center. We need one more. So let me copy paste it. So this is the another screen. This is S1 here and S2. As I said, S1 and S2 are the lead screens consisting pinhole at the center. So this monochromatic X-rays is passed through these two pinholes and here what we get is focused X-ray beam, fine pencil-like beam of monochromatic X-rays. So this is one part. Let me show the other one. What I am going to draw is round table. Here I am going to show a round table. So this is the round table. So the Bragg spectrometer, let me write that over here. Spectrometer consists round table. We are calling it turntable. And this turntable is capable of rotating around vertical axis passing through its center. So this is the turntable, and if this is the center of this table, then normal to the center is the vertical axis, and along that vertical axis, this turntable can move along the vertical axis, and this table has scale S and vernier scale. So the scale is marked on this table. So this is our scale from 0 to 360 degree, as it is a round table. And there are two windows in this. Let's say this is window 1 and this is window 2. Window 1 and window 2. So this is VS and this is also VS. You can say this is VS1, this is VS2. So through which we can take vernier scale reading. From the scale S, you will get the main scale reading, and from the vernier scale, you get the vernier scale reading. Then exact reading is main scale plus vernier scale reading. Whose vernier scale reading we have to take? Because at the center over here, the crystal C is mounted. Okay, at this point, this is the C, and C is the crystal mounted on table. Okay, in this case, C is crystal mounted on table. That is turntable. And so at any instant, we can find out the position of the crystal using the scale S and the vernier scale. Now to this turntable, a side arm is attached. So I am going to show here a side arm. This is the side arm. Okay, this is the sidearm. Let me modify this. Here is the C. C is the crystal. So this sidearm is attached to the turntable. Let me write here. Sidearm is attached to turntable, and this sidearm also rotates about vertical axis of turntable. So around the vertical axis, which is the normal to the plane, normal to the surface, passing through the center of the table is the vertical axis of that table. And around that vertical axis, this turntable can rotate. And also, this is the side arm which is attached to the turntable. This side arm also can rotate around the same axis. But in this case, the arrangement is such that, in this case, arrangement is such that if turntable rotates by an angle theta, then turntable rotates by an angle 2 theta. Such an arrangement is there for the side arm. Now let's see what side arm consists. This side arm consists a slit S3. There is a slit S3. This is the S3. And a ionization chamber. Let me draw ionization chamber here. This is the ionization chamber. And this ionization chamber is having two electrodes. And these two electrodes are connected to electrometer EM. This is EM and this is the ionization chamber. So let me write. Sidearm consists slit S3 and ionization chamber. Ionization chamber containing vapor of known gas. And consists electrodes which are connected to electrometer. So that is the construction. Now let us see how it works. Working of this Bragg spectrometer. As I said here, X-rays are produced by the Coolidge tube. They are passed through the filter, and when they comes out of the filter, we get monochromatic X-rays. And this monochromatic X-rays, let me use the another color. This is too bright. Okay. This monochromatic X-rays incident on the crystal C with an angle, says, let me redraw this crystal. This is the crystal C, and this angle, glancing angle, is theta. And when Bragg's law is satisfied, a strong X-ray beam is reflected and it enters into the ionization chamber. Now this ionization chamber consists vapors of the known gas. When X-rays pass through it, that gas ionizes and produce the ionization current. That ionization current is recorded by electrometer at particular theta. So at particular theta, ionization current is recorded by electrometer. Then by rotating this turntable, we can find out current for different glancing angles. Okay, we can find current, that is ionization current, for different glancing angle is recorded. Then a graph of current versus glancing angle theta is plotted. Let us plot the graph. This is the x-axis. This is the y-axis. On the y-axis, there is a current, and on x-axis, the glancing angle theta. And what we get is a graph like this. At certain glancing angle, we get the peaks. That peaks are due to constructive interference. And from these peaks, we can find the values of theta 1, theta 2, theta 3, etc. So the Bragg's law is what? 2d sine theta is equals to n lambda. Using this experiment, we can find the theta, at which theta you get the peak, that is the constructive interference. And if wavelength is known, theta is measured on the spectrometer, then we can find interplanar spacing. Once you know the interplanar spacing, we can find Miller indices of that plane.